Okay, student, we are going to continue the FWC paper discussion from where we left in the last class. So I was explaining the third statement. Okay, so it's about 4-level laser system. Okay, so it says 4-level laser system is more efficient than 3-level laser system. So I explained you that in 3-level laser systems, you have only 3 energy levels. But when it comes to 4-level laser system, just 4 energy levels. So in 3-level energy, 3-level laser system, let's say the energies are E1, E2, and E3. What is the special name given for this second level? What is the name given? It's metastable state. Okay, it is necessary to create a population inversion. So usually when you call it population inversion when more electrons are in the higher energy level, which is unstable when compared to the lowest energy level, which is stable. So this population inversion. So the special property of this metastable state is it can keep electrons in excited state for a little bit longer time when compared to the level E3. Okay, so that is the reason for why and stimulated emission is allowed in this case. So when you send a photon, so this photon will go and say, okay, hi, you want to come like me? You go to the ground level and you will become like me. So it will motivate these electrons, so they will come to the ground state again. And then what will happen? They emit this energy difference in form of a photon. So now this photon also has the energy of E2 minus E1. Now there will be 4 more photons. So altogether there will be 5. Okay. So now he has got some friends. So it will create a laser beam. All right. So they will be monochromatic, same frequency, same wavelength. They are parallel to each other, same color. Okay. That's how you produce this. So when it comes to 4-level energy, 4-level laser system, you have 2 possible metastable states. So it increases the efficiency because you can produce different laser frequencies and energies. All right. So that statement is correct. Okay. So A, B, C, all correct. All right. So I explained you about the pumping, optical pumping, laser media, and the resonator and all that in the last class. So you have to watch the recording if you haven't. Okay, you have to watch the recording. Okay, let's jump to the next question. The diagram shows variation of force with time acting on an object of mass 5 kilograms. If the velocity of object at t is equal to 0 is 1 ms minus 1, what is the speed at t is equal to 7 seconds? So in this question, the concept is very easy, but they have made it complicated because of the shape of the graph. Okay, so that is one unnecessary work they have done. I won't scold FWC, I think because I criticized in the last class, it went wrong. Okay, so with all due respect to the FWC papers, this question is a bit difficult because it has a little bit of difficult sum. Okay, otherwise the idea is simple. So you have been given force time graph. So how can you use a force time graph to relate it to the velocity? You have to tell me. Otherwise, I'm not moving forward. Yeah? Participate, please. Fatima Sajjad, what do you think? What do you think? Salma, what do you think? Force time graph. So if you have a force time graph, okay, the force time graph, you have to look at force as the rate of change of momentum. So if it is the rate of change of momentum, when you have a graph with time, then if you take the area under the graph, it will give you the change of momentum. The rate will not be there because you have multiplied by the t component. Okay, when you multiply this by this, you have multiplied by the time. So you have removed that rate thing. So it is now only what? The change of momentum. So you can find the change of momentum by calculating the area under the graph, and then you have to use your concept to find the final velocity. And you have to be very careful. There is a little bit of trick. There is something tricky here because they have given the graph up to 8 seconds. Okay. But the question is only until speed during the 7th second. So you have to be careful at that point also. When I did this question for the first time, I actually mistook that. But fortunately, there was no answer for that. So I again corrected myself. Okay. So if you find the area under the graph, the graph looks like this. Okay. So this is not a simple diagram. It's a composite diagram. So this has 5 sides. So you have to simplify it by dividing it into 2 simple figures. So now you have a triangle and a trapezium. Now you can find the areas of each and add them. Okay. So what is the area of this part? Did you all calculate? What's the area of this part? This one is 3. All right. This one is 3. This one is 1, and 2 is somewhere here. And here you have 7. And then here this point is, because we need that for the base. All right. This one is 1. Okay. So if you find the area, what did you get? That will give you the change of momentum. 6. Very good. So you get 6. I'm not going to waste my time with sums. Okay. We have to finish. The idea is the only important thing for us right now. And then if you find the area of this, what did you get? Trapezium. I got 6.5. Okay. So this is the total momentum change that occurred in this time period. So the total momentum, so total change of momentum will be equal to 6 plus 6.5, which is 12.5. Okay, which is 12.5 kilogram meter second minus 1. So you can find the change in the velocity by dividing it by the mass, because delta P is equal to m mass multiplied by delta V. All right. So now delta P is 12.5. You can find the velocity change and add that with the given value 1, the initial velocity. Or else, what can you do is you can directly apply delta V here. Okay, so m, I'm going to put what? 5 kilograms multiplied by, this is the velocity change, which is final velocity minus initial velocity, both in the same direction, so I don't have to worry about the plus minus. So I just put the minus that already exists in the equation. Okay, so if I find this and do all that, what is my answer? 3.5 meter second minus 1. Any doubts?
No, sir.
Okay, good. The next question is about the displacement time graph. Okay, so this displacement time graph is a very simple graph. Okay, I'm not going to draw this graph. This question is actually, I think it's mistaken. Okay. Fifth one. Diagram shows displacement versus time graph drawn for displacement measured from the moment when 2 particles A and B moving in a straight line. Okay, in a straight path, pass a particular point P. Consider the following statements. The first statement says acceleration of B is higher than that of A. Do you agree with that?
Yes.
Do you agree with
No,
that?
sir, no, it's more in the uniform velocity, sorry.
Yes, it's uniform velocity. So you cannot say that there is acceleration. Actually, acceleration is 0, right? So that statement is wrong. Both of them have 0 acceleration. But if they compare the velocity, of course, the B is higher. B is higher. The second statement, at time t is equal to t3, A and B meet together for the second time. So actually, that statement is correct. Okay. So in this case, they have given displacement time graph. So when they directly give the displacement, when 2 particles have same displacement at the same time, which is in this graph, the lines intersecting each other. Okay. So if you look at the graph, it is ST graph. Okay. So it goes like this, and then the B1 goes like this. All right. goes like this. So here you can see at this point, they have same displacement at the same time. Here also they have same displacement at the same time. So you can understand that they meet. Okay, so second time it's meeting at T3. So this is first time. So first time is at T1. Okay, second time at T3. That is correct. Okay, B statement is correct. And then after time T is equal to T3, the velocities of A and B are opposite to one another. Actually, after T3, what is the velocity of A?
That's 0.
Yeah, it is from T2 onwards, it's 0. Okay, so they can't comment about velocity. There is no velocity for A. So the statement is straight away wrong. Okay, so only B is correct, but the scheme says a different answer. I think it's A and C. Maybe they have taken this as maybe a velocity time graph, but still the velocities are not opposite after time T3. C statement should be wrong. I don't know why. Okay, so in the scheme, I don't have the scheme here, but I checked the scheme for Tamil medium. It says A and C. I don't know why. But the correct answer is B only. Okay, sixth question. The diagram shows a composite bar made using 4 different metal pieces in S shape. Okay, taking S shape. When heated up to 90 degrees Celsius, their coefficients of linear expansions are when heated up to 90 degrees Celsius, their coefficients of linear expansions are mentioned. If it turns to straight I shape, okay, straight shape, not exactly IE, it will be like a straight line. When allowed to cool down to the room temperature. So we can understand that at room temperature is tight, but at 90 degrees Celsius, it's bent. So it means that it has undergone expansion. So expansion is the only reason, explanation that we can give to this phenomenon. Okay, so it is a bimetallic strip. And you know, in a bimetallic strip, when they expand, when there is a difference in the linear expansivities. Okay, let's say this one has alpha 1 and this one has alpha 2. What is the conclusion that you can come up with? Which is greater? The one that has a higher length will have the greater coefficient of linear expansion. So, which one has the greater length? 1 or 2?
It's 2.
It's 2. Because if you take, they will have a center for their curvature. Okay, if there is a curvature, if you complete a circle, there will be a center. Okay, so for this circle, the radius is higher than that of for this circle, right? So the perimeter of this circle will be definitely higher. So this has a higher length. So you can say alpha 2 is greater than alpha 1. So like that, you can comment about this. So in this diagram, in the above part, alpha 1 is outside. Okay, the outside one expands more. That is the theory. So alpha 1 should be greater than alpha 2, and alpha 4 in the below one is greater than alpha 3 because 4 is outside. Okay, so the correct answer is fourth one. Okay. Seventh question. Two prisms of refractive indices N1 and N2 are kept in contact as shown in the diagram. N1 and N2 are in relationship with the wavelengths lambda as follows. N1 is equal to 1.2 into blah blah blah, and N2 is equal to this. Okay. If the value of lambda for a light ray incident angle to pass without refracting on BC is lambda naught, which gives lambda naught. So did you understand this question? I didn't understand this question, but I changed the question and did the steps for my question, and I found an answer. The answer is correct. Okay. So can you change the question? Can you write it like this? If the value of lambda for a incident for any incident angle to pass without reflecting, which means the total internal reflection not to happen, okay, not to happen on BC, is lambda naught. What gives lambda naught? So did you understand? For any incident angle, it should not undergo total internal reflection at the interface between the first and the second prisms, okay, which is BC. At BC, it should not undergo total internal reflection. So what is the condition that should be there at BC not to undergo total internal reflection? At BC, the incident angle should be smaller than what? It should be smaller than the critical angle. Come on, guys. Okay. So we should find out what is the value of lambda, because the lambda will determine the refractive indices. Refractive indices change according to the lambda. You can understand by sending white light to a prism. It creates a spectrum of colors, right? Vibgeo. So that is due to that phenomenon. Okay, the lambda, when lambda is different, the refractive indices are different and the deviation is different. So they will be seen separately. So like that, here they have given the relationship with lambda and they're asking which lambda will produce no reflection at all at any incident angle in this space. Okay, we call incident in the first, we call it incident ray for the first ray, right? Okay, so I will use a random situation. So let's say it goes like this and it goes like this. Okay, so it's a random ray, but I have to find out for any ray not to undergo total internal reflection. Okay, so now imagine I am moving it like this. Okay, I'm moving it like this. If I send the ray like this, it will be like this. Okay, the reflected ray in the first prism will be like this. So what happens to this angle of incidence on this BC surface when I take this ray downwards when compared to this one? This is here, this is a bit down, okay, which means I'm increasing the incident angle here. Just like this, initially the incident angle, now the incident angle is this. So when I increase the incident angle here at this point, in this interface, here what happens? The incident angle decreases, right? You can see. If I move further, incident angle will further decrease. Okay, you can see it's getting smaller and smaller. So when we are moving in this direction, which means when we are increasing this incident angle, we don't have to worry about total internal reflection because it is getting smaller. The angle is getting smaller. So we don't have to move in this direction. We have to move in this direction because when you move the ray in this direction further and further like this, here the angle of incident will increase. So now we fear total internal reflection. The angle is increasing. What if it goes to C? If it is critical angle, it will undergo total internal reflection at the next possible point. Okay, it will be barely going through the interface at critical angle. If you increase a little bit, what will happen? It will undergo total internal reflection. So we are worried when we are moving the ray in this direction. Okay, that concept should be very clear. So now, to make sure that it never undergoes total internal reflection, what should you do? You have to create a maximum angle here Okay, you have to create a maximum angle here. Okay, maximum angle here, and make sure that it doesn't undergo total internal reflection, or it barely undergoes total internal reflection, which is the critical angle. Do you understand that concept?
Yes.
Yeah, you have to take the maximum point. So when you're moving in this direction, it will go to the maximum, right? So what is the possible lowest incident angle here? Hmm? Come on. 0, right? Possible lowest incident angle will be 0. So I took it as 0. So when I send it with 0, it will go here and hits. If it is less than C, it will never undergo for any angle. This is the highest possible incident angle here. So it should be C, because we take the margin. Okay, we take the barely it undergoes. Okay, so at that point it will be like this. Okay, at that point it will be like this. So now what would be the incident angle? This is 60, this is 40. What will be this angle? Total should be 180, so it's 80, right? So it is 90, because the incident angle is 0. Incident angle is the angle that it makes with the normal, so it's 0. But this angle is 90. It is along the incidence. Sorry, normal. What will be this angle? 80 plus 90 is 170. This will be 10.
10, 10,
This will be 80.
80.
Okay, for 80, it should not undergo total internal reflection. So now write the equation for this critical point. Okay, you know n sine C, n1 sine C1, or you can write n1 sine C is equal to n2 sine 90, which will be 1. We don't have to write, or you can just write it. Okay, so this is the theory. So n1, what are you going to put? 1.2 multiplied, sorry, 1.2 plus. Okay, the sums are the annoying stuff, but let's do. With 8 multiplied by 10 to the power of 4 divided by lambda squared. Okay, sine C is sine 80 degrees. That's again annoying. And n2 is 1.45 plus 1.8 into 10 to the power of 4 divided by lambda squared. So actually I approximately took this sine 80 value. It was 0.98, but I took it as 1. Okay, I just took it as 1. I just took it as 1 because it's closer to 1. And if when I solved, I got for lambda 600 nanometers. That is the scheme answer. So I think this should be the question. Okay, the question they intended to ask was what I said, not this. This question doesn't make any sense, right? This way, if you have any ideas, you can share it with me. Do you have any? Okay, so let's go to the next question. This is a very famous question. There were a lot of questions like this. The famous one is 2005. 2005 question. Go and try that. Okay. Okay. Question number 8. Figure shows a system of metal piece attached to the external of a metal vessel floating in the water inside a beaker. Suddenly, the metal piece falls off the vessel. Consider the following statements. Okay. So now it is a bit different from the past papers. This is one of the good questions in this paper. Okay, so there is this beaker, it has some water, and inside that there is this vessel that is floating, and it has a metal piece. The only thing that I didn't understand was whether this metal piece is completely an enclosed one, or it the water will enter this when it gets dislodged from this vessel. That is the only doubt I had, but I took it as a closed one. Okay, let's do that. So now it gets dislodged and it goes to the bottom, let's say. So now you don't have this metal part with the vessel. Okay, so the first statement says, since the volume of water displaced by the metal piece doesn't change, the water level in the beaker will not change after the metal piece falls off. So first of all, will it change or it will not change? So here also it was displacing its own volume, right? Because it is totally immersed inside water. So this metal piece was already displacing its own volume. Now it has fallen, it will still displace the same volume. But the problem is, initially it was floating, now it has immersed. Okay, it's no longer floating. Okay, so it means that initially when it is floating, it was displacing its own weight. Okay, so let's say the weight of this is metal part. Okay, so it has air inside it, but let's say the total weight is W. It was V rho G. This is what it was already displacing. So let's substitute. Let's substitute mg for this, and mg will be equal to V rho G, right? So I can't say a specific volume because it has some metal particles inside a metal piece. But I can consider a resultant density for this. And I can just put its own volume, let's say V naught, and write. Okay, so V naught, resultant volume, rho. So if I say resultant, that will do. Okay, V rho G. All right, equal to V rho W. Sorry, here I'll put W, WG. Okay, so this was the volume that was displaced. This V was the volume that was displaced when it was floating. But now it will displace this V naught because now it has immersed. So it means that the upthrust is not giving its weight. But initially it was floating. It means the upthrust was somehow giving its weight. Now it's not giving its weight. It will just displace V naught. Which is greater, V naught or V? Just think about the equation. G common for both sides. This rho, the resultant density of this metal piece is higher. Here, rho W is less than that of the metal piece. Okay. So to balance the equations, this should be greater than this. So V naught is less than V. So initially it was displacing V, which is the volume of water that will equal the weight of this. But here it is displacing the volume of its own, which is less than this, according to this equation. So the water level should go up or down? Should go down. Now it is displacing smaller volume. Okay, guys. So this is what happens when a floating object all of a sudden immerses. Okay. All right. So here they say the metal piece falls off. It means that it goes down. So the first statement is wrong. The B statement says when the metal piece in the beaker is put inside the vessel. So now it has fallen now. Now you are putting it back inside the vessel. Inside the vessel. So initially also it was attached here. Now you are putting it inside the vessel. So when you put inside the vessel, it will again float. So again, this equation can be applied because when it is floating, it is displacing the volume of water that is equal to its weight. It displaces its weight. But when it immerses, it displaces its own volume, which is less than the volume that is displaced when it is floating. So now it's going to float. So when you take it back and put it inside, it's going to increase. The water level is going to increase. So that is correct. C statement says, because of the volume of water displaced by the system is high, when the metal part was attached to the vessel, the water level of the beaker decreases when it falls off. That is the exact explanation I gave you at first. Okay, so that C statement being correct directly makes the A statement wrong, right? So A is wrong, so B, C correct. So the answer is the third one. Any questions? Any questions? So remember, the summary is, when something is made, when some denser object is made float, it will displace its weight, the weight of water that is equal to the object's weight. That particular volume will be higher than the volume of the object itself, because object is denser, so smaller volume is enough to make that particular mass. Okay, but the same mass to be made, or the weight to be made by water, it's a higher volume, because water has low density, right? So
Yes.
due to that, when it floats, more water. Remember like that. When it floats, more water displaced. All right? That is a summary. You have to write it in your notebook or something, because those kinds of MCQ points will help you. Okay, the next question is about siphon. Okay, it's not a pump. It's a pump, kind of a pump, but it is a siphon. Siphon is the exact term word. Okay, the siphon is a very beautiful principle. It was introduced to our syllabus in 2011 prototype paper, support seminar paper. 2011 support seminar paper, there is a hydrostatics MCQ. The mechanics MCQ was on this. Sorry, MCQ, not MCQ, essay. 2011 essay prototype paper. The paper that is given by the government, okay? People call it department papers. So that paper has its beautiful essay. I don't have the English medium paper. If you have, you can share it in the group, okay? Somewhere, maybe the Electron Academy Tesla Telegram group. Okay, so now the ninth question, figure shows a pump filled with liquid of density rho. Respective heights are noted. Assume that the atmospheric pressure is P naught, considering the following statements. So usually there should be one additional information that you should give. They should give something like the container has copious amount of water, or the surface area of the container is very large, or something like that, because we always take the surface of the water in the container, or the water level in the container is not moving. The velocity of the water level in the container is 0. Usually we take it like that. So they should express in some way that the water is a lot and the movement of the level will not be observed when this pump works. Okay, so that is an additional statement that should be there. But anyway, we shall take the velocity at the water surface as 0. Okay, okay. The A statement says, okay, I will explain you the physics of it first. Okay, so yeah, you have this. Very great drawing. Okay, so this is the principle. Okay. So the siphon tube has a uniform cross-sectional area. Okay, here the uniform area is there everywhere. So when you apply the equation A1 V1 is equal to A2 V2, the continuity equation, the velocity throughout the tube will be equal, because the surface cross-sectional area is equal. Okay, so let's say that it enters with v velocity here, it goes with v velocity here. Everywhere it's v. Everywhere it's v. Okay. Yeah, they have mentioned some points, and here they say it's point A. Okay, please ignore the sounds. But actually, I think they should have given P, Q at the same level like this Q and R, because the statements discuss about PQR. Okay, so there is some mistake. Yeah, this height is H2, they say, and from this point to the top of this is H1, and the height from here to here is H3. All right. Okay. Yeah, it finishes at the same level as the bottom of this, but that's fine. That doesn't matter. Okay. So now they say A statement H3 should be greater than 0 for the pump to function. Is that correct?
No.
Yeah, that is correct. Okay. So the purpose is to take water from here. So the velocity of the water cannot be 0. It should be greater than 0. That is the principle. And this flow can be considered as a streamlined flow. We can apply Bernoulli's equation. All right. So usually I advise you to apply the Bernoulli's equation from here, from the surface of this large container to whatever the point you consider. Okay. So as this is relevant, I'll take this point as X and this point as R, and I'm going to use Bernoulli from X to R. Okay. So Bernoulli says the sum of pressure plus kinetic energy of the unit volume plus the kinetic potential energy of the unit volume will be constant, right? So at X, what are the values of those components I just said? At X, pressure is P naught, atmospheric pressure will be there. So let's take this as the 0 potential level. So the height will be measured from here. So what is the height here? At this level, it should be 0, right? So H rho G will be 0. Half rho V square will also be 0 because we took this level as not moving. Yes. And then at the point R, what is the pressure? Atmospheric. Whatever that is exposed to atmosphere will have atmospheric pressure. Plus, will there be a HOG there? Yes. This is the level, and this level is H3 height below this level. So it should be expressed in negative values. Whatever below the zero potential level is negative. So minus H3 rho G plus half rho V square. Cancelled out. And now if you take this minus to this side, it will be plus. So H3 rho G is equal to half rho V square. So can you see, for the velocity to be a non-zero value, which means the water to come with some velocity, H3 should be greater than 0. It cannot be 0. So H3 should be greater than 0 for V to be greater than 0. Okay, note it down. I have applied Bernoulli from this level to this level. Okay. Okay. Okay, the next statement is pressure at point Q is equal to P naught minus rho GH3. Okay, so we can apply Bernoulli from X to Q. Okay, I'm applying X to Q. So at X, you know everything. P naught plus others are 0 is equal to, now for Q, we don't know the pressure at Q. It's not exposed to atmosphere now. So I will take the pressure at Q as PQ. That is the unknown thing that we have to find out. What is the velocity? It should be half rho V squared. What is the H rho G at that point?
H1.
Yeah, it is 0 again. Okay. So PQ will be equal to P naught minus half rho V square. And we don't know what is half rho V square. We have to take that also in terms of the heights. So half rho V square is equal to H3 rho G, right? Here, this equation says that. So P naught minus H3 rho G. That's what exactly given in the statement. So that is correct. The first one correct. Second one is also correct. Okay. Third one, flow speed of liquid at point R is equal to 2G H3 minus H2 at point R here. So you can make it a subject and C. So these two cancelled out. So V is equal to 2G H3. So that statement is wrong. Velocity, not only here, everywhere inside the siphon tube is this. Okay, so the correct answer is AB only. So third answer. Okay. Okay, 10th question. When the temperature of a liquid of a small volume is measured by, please underline that small volume. Small volume is very important. By a correct calibrated mercury in glass thermometer, its reading was 79.7 degrees Celsius. So it is showing some value there, but they say the actual temperature of the liquid is 80 degrees Celsius. So it's showing a wrong value, less than the original one. What is the reason for this difference? Okay, so when it comes to a mercury in glass thermometer, when it is correctly calibrated, we can't say that it's due to wrong calibration. They have considered everything, every factor that is usually considered in manufacturing and calibrated it correctly. Okay, you might say it might not have a uniform expansion. No, that will not affect, because when manufacturing, they draw a graph. If it is not uniform, the calibration will not be uniform either. The graph goes like this. Now you know, okay, it doesn't have a uniform expansion. Then you will reduce the length between the subsequent points in the calibration also. So you will correct that. During the manufacturing. Okay, and they also say another statement about the expansion of the bulb. That mistake will also be corrected during manufacturing. Actually, what they use is apparent expansivity. So when you use apparent expansivity, you consider what you observe. Okay, it might expand a little bit, but that error is corrected during the manufacturing. So they will put it inside 50 degrees Celsius and let it raise, and then they mark 50 there. They accurately do that. Okay, so whatever the error that can come is corrected during the manufacturing in a correctly calibrated thermometer. So why is it showing a low value? What could be the possible reason here? Because it's measuring small volumes. That is the problem. If you take the accuracy of a mercury in glass thermometer, accuracy is very, very low. Okay, it's not very accurate. Because what is meant by accuracy? Showing the correct value. So accuracy is affected by the temperature absorbed by the thermometer. Okay, so if you are using it to measure some liquid at 90 degrees Celsius, what should happen? The physics that happens here is this liquid should give some heat to this mercury. Then that mercury will expand. When it expands, you will see the rise in the mercury levels. Okay. So when you give heat to this mercury, which is very small amount, you will give a very small amount of heat. There will be some heat lost due to that process itself. So this is 90 degrees Celsius temperature, but after giving some heat, is there a possibility for the temperature to fall? Is there a
Yes.
possibility? Technically, yes. When you give something, that should reduce, right? Okay, the heat should reduce. When there is a reduction in heat, delta H or delta Q or whatever, is equal to MC delta theta. MC will not change. When there is exchange of heat, there should be a difference in temperature. That is inevitable. That will definitely happen. But why we are using the mercury thermometers? Because you give a very small amount of heat. So this delta H is negligible, very small. And the amount of substance that is being measured is very high. You measure large amount of liquids. So this is very high. So this is low. This is high. So this one, when you look at the equation, this should be very, very low, right? So we can neglect that error. The error will be there. Technically, yes, there will be delta theta, but it will be like 0.01 or something. Okay. So due to that, we don't usually take that error into account. We just say it's measuring correctly. But when it comes to small amount of liquids, you are reducing the mass. So it already has less heat. Okay. So it already has less heat. When it gives some heat, definitely it's going to affect its temperature. Because in that case, delta H is equal to MC delta theta. This is small. Even though this is small, this is going to be significant. Okay. So reduced volume is the only reason here that it has gone wrong. So according to me, the only correct answer is B only. But in the scheme, they have given C is true, but at least they should have given maybe BC, fourth answer. Or B only if it was there, that will be the correct answer. Definitely, I think with the experience with the past papers, I think that is B only is the correct answer. Because the expansion of the bulb, those things are considered during manufacturing. Otherwise, we will be using wrong thermometers. Okay, practically the uniform expansion is not achievable. Everything has a non-uniform expansion. We have better ones, but there are no ideal ones. Okay, so always these are corrected during the manufacturing. So that will not affect. When they say correctly calibrated, it is correct. But the problem is that small volume. Okay. So what is the thermometer that can be used to measure small volumes? Any ideas about that? Any ideas?
Digital thermometer.
Digital. Okay, maybe. I don't know the principle in digital, but one of the traditional ones that we can use is thermocouple. Okay. Thermocouple has a, so you immerse this copper iron junction into small amount of liquid. This part of the thermocouple is like a point and it will not absorb a lot of heat. So you can use it to measure the point temperatures, temperature of a surface, temperature of small amounts of substances possible. But mercury thermometer, it needs a volume for the bulb to be immersed. It should also be significant volume because the accuracy will be high only if it is higher volume. Okay. The 11th statement, sorry, 11th question. I'm not going to discuss about these optical instruments much here. Let's just look at the statements. Okay, you just go and revise. Consider the following statements regarding the compound microscope and astronomical telescope. Statement A says, the distance between lenses in a compound microscope in normal adjustment is larger than its state during the infinity adjustment. So, you know, the distance between lenses. So initially there are, you know that there are two lenses. The objective will produce a real image, the magnified one. Okay, so these are the Fs and 2Fs of the objective. And this side also you will put, okay, 2f0. So you keep the object here and it will produce an inverted magnified one. Okay, upside down, inverted magnified true. Okay, a real one. And here usually this image falls inside of the focal length of eyepiece. So it produces a magnified, you call it erect, okay, erect image. Erect image. But when you are creating the image at infinity, you need image at infinity when you have to observe the observe the image for so long, because when it is at infinity, your eye muscles are relaxed. So at that instance, you have to make this first image to fall on this focal point itself. So you have to move the lens towards this side. Okay, you keep it here and the FE will come here. Now it will produce image at infinity. Okay, infinity. So that is what happens. So infinity, it will be magnified. We can't say whether it's virtual or real. For infinity, we don't say that. Okay, it's like in between virtual and real. Those are the properties. So you can see the distance between the lens should be increased to create an image at infinity. So that statement is wrong. B, angular magnification of astronomical telescope during normal adjustment, that is f0 over fe, is larger than that of its abnormal adjustment. There is no one abnormal adjustment. Okay, abnormal is everything other than normal. But I think what they mean by abnormal adjustment here is getting the image in the near point, which is 25. So when you get the image at 25, the angular magnification will be higher than at infinity. But we don't use that magnification. Why? Even though it's magnified, we always keep it at infinity. Why? Because your eye muscles are relaxed. When it comes to astronomical objects, you have to observe that body for so long sometimes to assess the movement of the celestial bodies. So the time duration is high for the eyes. You have to keep it at infinity. C statement, eyepiece acts as simple magnifying lens in both compound microscope and astronomical telescope. That is wrong. In astronomical telescope, it's not. When they just tell the statement, we have to take it as normal adjustments. Okay, otherwise we can't answer. So if we take it as normal adjustment in compound microscope, yes, it acts as a simple magnifying lens. But when it comes to astronomical telescope, that is not true. It's at focal point, so it will be at infinity, the image. So A, B, C are incorrect, but in the scheme they have given C. Okay, they have given C. Any queries? Okay, 12th one. An object of mass 10 kg moves along the curved smooth path AB from A at rest and then moves along the horizontal rough path BD. Okay, it's rough, so there will be friction there, as shown in the figure. The coefficient of dynamic friction between the object and the flow is 0.1. Collides and joins and moves with the spring constant 2 into 10 to the power of 4 Newton meter minus 1. At the point C, it rests momentarily. Then what will happen? The constricted spring will start to stretch again and then it will go. So that will be a momentary rest. The maximum compression that could occur in the spring, neglecting the energy loss during the collision, is what? So we have to use law of conservation of energy. That is very simple. I'll just write the equation for you. You can solve it. Okay. So let's say I will draw the position when it has come to pressed momentarily. Okay, so with the constriction, so the spring will have weight here, the object started to constrict the spring from here. Let's say the spring's initial position was here. So now it has constricted and come to this. So this is the constriction of the spring, and this is the rough length that it has moved, 10 meters. You should understand that from here to here also, the x distance also, it has moved in a rough path. So that loss of energy should also be taken into account. And this is the mass at the initial position. And from the, so let's say this is zero potential level. From the level, height initially was 10 meters. Okay, so use law of conservation of energy from here directly to here. So I will use, so total energy at EA is equal to total energy at, let's say this is B, no, B, DE, let's say X. X, total energy at X plus the energy lost in what? Friction multiplied by distance. That should be, yeah, otherwise you will get it wrong. So this will be MGH. M is 10 and G is 10, H is 10. This one is the energy stored, elastic potential energy, that will be half KE squared, right? So half KX squared. So half K is 2 into 10 to the power 4, X squared, you don't know. Plus F into D, F will be mu R, okay? So coefficient of friction 0.1 multiplied by R, which is 100. Am I right? 10 kilos, right? So it will be 100. Mu mg multiplied by the total distance moved 10 plus x. 10 plus x. Okay. So it comes like, you cut all the tens. Here 100, here 10 to the power 2. Here, so it will be 10. Half. So a 2 gone. So 100 x squared plus this will be 1 plus this will be 0.1 x. So it is negligible, right? This is 100 x squared, this is 0.1 x, so this is negligible. So you take it to this side, it will be 9 equal to 100 x squared. We have already neglected this. So take all the square roots here, and then you will get x is equal to 0.3 meters. Okay, so the correct answer is third one. Okay, any questions? Okay, the next question is, yes, but yeah,
No doubts.
no doubt. Good. I will take it as there is no doubt because you have understood it fully. You know, always there are two possibilities. No? Two stationary sound sources, S1 and S2, generate sound waves of frequency 165. The figure shows cars moving towards S1 with a speed of 20. So moving towards S1 and moving away from S2. Okay, the figure shows car moving towards S1 with a speed of 20 ms minus 1 between them. What is the beat frequency heard by the observer in the car if the speed of sound in air, should be air, is 330. Okay, so now moving towards 1 and moving away from 1. So let's say F1 is the frequency by S1. F1 is the apparent frequency heard for the sound by S1. Okay, so F1 is equal to what? when the observer is moving, you change the velocity, okay, above the numerator of the equation. So you have to put F1 is equal to 330 plus what? 20. 330 and multiplied by the original frequency. F2 is going to be like 330 minus 20 divided by 330 multiplied by 165. Here, what is the answer? 2. So it's 360, it's 180 hertz. What is here? 150 hertz. Am I right? Sorry. It is 350, no? So it should be 175 hertz. This is 310, so it should be 165 hertz. Sorry, 55 hertz. So the answer is, you do the sum, it's 20 hertz. Okay. The fourth one, a stretched string is vibrating at its fundamental frequency. If it is made to vibrate at fundamental vibration after increasing its tension by 69% and reducing its length by 35%, what is the ratio between the final and initial fundamental frequencies? So, you know, the equation for fundamental frequency, F is equal to 1 over 2L square root T over M. So here the two factors that are changing are L and T. So you can say F is directly proportional to square root T over, sorry, L is outside the square root, no? Square root T over L, right? So this is the initial, let's say F1. Final will be, you have increased the tension by 69%. So initially if it is 1, finally it will be 1.69, right? So it will be 1.669 T. Okay. And then L is reduced by 35, which means now it is, initially if it is L, now it should be 0.65, reducing it by 35%. So you solve this, you will get the answer 2:1. Okay, 2:1. So this is square root of 13. Okay, 169. So it's 1.3, it's 0.65, it's 2, right? Then the 15th question. A biconvex lens of focal length 30 centimeters is divided into two equal parts made into two plane convex lenses. It's not in the syllabus, but they have divided. So what will happen to the focal length? They will still function as convex lens with individual focal lengths of 60-60. That is the concept. Okay. They are placed together and the interspace is filled with water, which looks like a concave lens. If the image of a point object placed on its principal axis at 40, from the optical center of this compound lens forms at infinity, what is the focal length of the water lens? So what is meant by getting the image at infinity when you keep it at 40? It means that 40 centimeter is the resultant focal length. So the new focal length is 40 centimeters. This is a combination of three lenses, two 60-60 convex lens and one concave lens. So you say 1 over 60 plus 1 over 60 plus 1 over unknown, okay, equal to 1 over 40. Is it difficult? No, right? You take it to that side. 1 over f is equal to, you can take the LCM 120. This will be 3 minus 2 minus 2. So then f will be equal to minus 120 centimeter, which means concave. Okay, concave 120. The answer is fifth answer. Any doubts? So the main principle is when you divide a convex lens through its symmetrical axis, there will be two individual plane convex lens with twice the diameter of the initial convex. Okay? Because there is only one convex surface. So it will find it difficult to converge. So it will be doubled. The length will be doubled. Okay. Next question. Three particles of mass. I will stop here. I will discuss the rest of the questions in another day. Okay. 16th one. Three particles of mass M are attached in an equilateral triangular shape by three identical springs as shown in the figure and are placed on a smooth horizontal table. So there is no friction. Length of one spring when unstretched is L. Now the table is rotated with angular velocity omega about the center of the mass of the system. Okay, which will be the midpoint of that triangular shape, right? Yeah. Now the table is rotated. Okay, we read that. If the distance between two masses becomes 2L, at this instance, the spring constant of one spring is given by. Okay, so now what kind of motion does the objects perform? Abhishankar? What kind of motion is that? It's a circular motion, right? So a circular motion requires a centripetal force. So what is the force that gives the centripetal force here? Salma? Umar Tahzaz, nice name. What gives the centripetal force? It should be the tension because there is no friction. So the only force is the tension in the springs. So initially unstretched length was L. Now it has become 2L, which means that the extension is L. Okay, L became 2L, so extension is L. So the tension is KL according to Hooke's law. All right. So now we have to apply the theories we know. Okay. So these are in triangular shape. I'm going to just draw the forces. Okay. So this will be the force given by the string on this, or the same mass by the other string. So like that, they will have their forces. So when you do such question, you can select one of the masses and apply because the system will work the same way for each. So I will take one here, the top one. All right. So I will draw the triangle, which is an equilateral triangle. And this is the center, and this is the mass. So now you have a force KL here, another force KL here. So how do they give the centripetal force? These two forces will have horizontal and vertical components. Okay. When you look at it, you can say this as vertical component, this as horizontal component. Okay. So the horizontal components will cancel out each other. The vertical components will produce the resultant in this direction. So you know that resultant will be 2KL cos theta, provided that the theta is this. So this will be 2KL cos theta. Okay. So that will be equal to 2KL cos theta is the only force. So that should be the force that is giving the centripetal force, which is M omega squared R. So here we don't know R, we don't know theta, a lot to do. So here you can take it as 2KL, 2KL. What is theta here? This line will bisect this angle. Angle of the equilateral triangle will be 60. So theta is 30. So cos 30 is square root 3/2. M omega squared. R should be expressed in terms of L. So this is R. Okay, this is the distance from the object to the center. So this is R. So how can you find? You can construct a triangle like this, a right angle triangle. Okay. So the principle says if you complete this bigger triangle, this is radius, this is radius. So this is an isosceles triangle. When a straight line is drawn to the base of the isolateral triangle perpendicularly from this point, that will bisect this line. We studied that in grade 9. So if this length is 2L, this half of this will be L. Sorry, it's a lot of letters here. The length will be half of that length will be L. Okay. So you can find out this R using this angle, right? You can use, this is adjacent side, this is hypotenuse. So you can use cos again. So cos theta is equal to adjacent side, which is L, hypotenuse, which is R. So this is cos 30, right? So square root 3 by 2 is equal to L by R. So R is equal to 2 square root 3 L. So I'm going to substitute it here. So 2 divided by L. Okay, if I ask you, have you ever seen a similar question like this? Which year was that? That was for masses. So you used gravitational force. What year was that? 2020. Okay, go and do that. So you cancel 2, this 3 will come here. Let's cancel L also. So the question is the spring constant K. So you take this here. So you have M omega square. There's a 2 and square root 2, square root 3 will be 3. So the correct answer is 2 by 3 M omega square. So the third answer. Okay. Okay. I have to go to a program. Okay, I'm sorry. We shall discuss. There are a lot of questions. Due to the complex sums, it takes a lot of time to discuss one question. Otherwise, the questions are simple. Any doubts from what has been discussed up to now? Okay, thank you.